So, in a world full of really complex problems, who are the people actually building the solutions? Well, today, we're going to pull back the curtain on what it means to be a modern engineer by taking apart one person's actual career journey. We're going to use their public research to build a kind of blueprint for innovation itself.
Okay, let's be honest. When you picture an engineer, what comes to mind? Is it somebody hunched over a circuit board? Maybe a specialist who's totally locked into one super narrow field? The reality, it turns out, is way more dynamic and, frankly, a lot more interesting. So what does it really mean to be an engineer today?
To answer that, we're going to dig into one key source, the public research profile of Professor Zeeshan Khan. By just tracing his journey through his published skills and papers, we can pretty much map out what a career in modern innovation actually looks like.
You know, every great journey has a starting point. And for an engineer like Professor Khan, that journey doesn't begin with some huge, sweeping system. Nope. It begins by mastering the invisible world, the world of the microscopic. This is where the whole foundation gets built.
The very first thing that jumps out is just the sheer depth of focus. We are talking about the fundamental physics of how all electronics work. Stuff like semiconductor physics, nanoelectronics, literally building materials at the atomic level. This isn't just a casual overview. This is a deep, specialized expertise in the science of the incredibly small.
So what does that expertise look like in the real world? A great example from his work is the MOSFET. The easiest way to think about it is like a microscopic light switch. I mean, it's so tiny you can fit billions of them on your fingertip. Understanding how to build and improve this one tiny switch is absolutely fundamental to creating every single piece of tech we all rely on.
And this kind of knowledge, it was forged over years of intense focus. His profile lays out a really clear timeline. Starts his PhD in 2010, publishes some highly specific research on core components in 2016, and then finishes his PhD in 2017. This whole period was all about going deep, not wide.
But okay, this is where the story takes a really fascinating turn. How does someone who masters nanometers, these tiny, tiny scales, apply that knowledge to something as massive as our national power grid? It's a huge leap in scale, and it really starts to redefine what an engineer can even be.
And this is that leap in scale we're talking about. He takes his foundational knowledge, the physics of microscopic transistors, and applies it to these massive, real-world systems like power grids. The big insight here? Understanding the small is actually the key to controlling the large. If you know how to make electrons flow efficiently in a tiny little chip, you can use those exact same principles to make electricity flow efficiently across an entire country.
And this isn't just theoretical stuff. His profile shows how that deep understanding of materials and energy efficiency translates directly into large-scale impact. He's consulting for solar and hydropower projects, he's researching risks to our power lines, and he's analyzing how to make our energy grids smarter. It's a direct line from the physics of a single transistor to powering our world.
Okay, so we've seen the path from nanoscale physics all the way to the national grid. That's a pretty logical progression. But what comes next? This is the most surprising part of the whole blueprint. A massive expansion into fields you would just never expect. So get ready for this.
Suddenly, his name pops up on a paper about blockchain. You know, the secure, decentralized tech behind cryptocurrencies. But he's applying it to manage the agricultural food supply chain. This is the first clue that his foundational skills are becoming a kind of launchpad.
And then a complete pivot into cybersecurity. He's co-authoring research on using AI to detect DDoS attacks. That's when hackers just overwhelm a system with traffic to shut it down. So from semiconductor physics to fighting hackers, how does that happen?
And just when you're trying to process that, his work expands again, this time into machine learning for natural language processing. He's working on sentiment analysis, which is basically teaching a computer to understand the emotion behind words. For the Urdu language, this is pure data science.
And why stop there, right? Let's go underwater. His profile shows work on the complex physics of communication for underwater sensor networks. It's another highly specialized and what seems like a completely unrelated field.
Finally, we see a paper that starts to connect all the dots, using the Internet of Things, or IoT, for smart farming. This brings together his expertise in energy, electronics, and now complex data networks, applying it all back to a real-world system like agriculture.
So what are we supposed to make of this incredible journey? I mean, from transistors to tractors, from power lines to programming languages, it looks random, but it's not. It's a pattern. It's a blueprint for how modern innovation actually works. So the whole thing really boils down to this three-step process.
First, you build an incredibly deep foundation in one core principle. You master it. Second, you apply that expertise to solve big, real-world problems in a related field. And third, and this is the magic part, you use that problem-solving mindset, that foundational way of thinking, to expand your horizons and attack complex challenges in completely different domains.
This idea, which is really synthesized from the focus of his profile, it just says it all. The mastery of energy and materials at the smallest scale didn't lock him into one field. Instead, it became a universal key, one that's capable of unlocking problems in agriculture, cybersecurity, AI, and way beyond.
Which leaves us with a final and pretty fascinating question. If this interdisciplinary, expansive path is the blueprint for a single modern engineer, just imagine what an entire generation of them, armed with this exact same approach, will be able to solve. What boundaries are they going to erase next?